Alright guys, so in the second video series of this method of characteristics, we're going to look at how you can actually find the x and y locations of each point. Alright, so just to start, again, we are looking at the first characteristic line. So just to start, let's look at point A, and let's place this point A at x naught as 0 of 0 and y naught equals 1. Alright, now we know that we actually found from previous video and also in class that this slope is equal to minus 73.3 degrees, and I hope you guys can calculate the line from here, right? So we know the equation of the line, and the only issue is we need to find what b is. Now we can see that the y-intercept of this line is at y naught, which is basically 1, right? So you are rewriting basically the slope equation in terms of b. You will get ba equals ya minus this, but that equals y naught minus the slope times x naught, but in this case our x naught is 0. So you end up getting y naught, right? So basically your BA is y naught, right? And similarly, here you have the equation. So all you're doing is solving for what is the x1 location at this point 1 is, right? So when you solve for it, at this point you will actually get x as equal to 0.3 and y1 is 0. Well, that's easy, right? Now let's look at point 2. Now I zoomed in because there's a lot going on, and you need to understand this for you to code, right? So I zoomed in this area. Let's look at the right learning characteristic, which is YA. Now we're looking at the second mark line coming right here. So this is the mark line we're considering, right? Here's slope of the line, which makes sense, and we saw from earlier that the BA intercept is always going to be y naught because it's always intersecting at the same point, right? Now, if you notice, I put x2 here because these two lines coincide at the same x and y location, right? So that's why I have the x2 points right here. Now, let's look at the equation of line for this blue line, this left running characteristics. So you get y2 is mu slope of this 1, 2 times x2 plus b2, right? Now we have to know what this b2 is in order to solve for this equation, right? So let's rearrange the same equation. B2 is y2 minus this, but hey, the same line passes through point 1, so that means it has to satisfy the point 1 as well. So I'm going to substitute y1 minus mu 1 2 times x1, right? So therefore my final y2 equation, I can write that as this equation right here. Okay, so all I gotta do to find x2 is equate ya and y2, right? I gotta equate this equation and that equation and basically solve for x2. So when I do that, you will get right here, right? So again, make sure you understand the steps, even though I put some numbers here. When you code it, you really have to know, you really have to understand what it is that you're coding, right? Otherwise, it won't make much sense. So here's, x2, I basically solved for x2 from this equation to here, right? And once you get x2, your y2 will be just this equation, right? So when I can rewrite this y2 equation as mu 1 2 x2 minus x1 plus y1, and we already found x1 right here, and that equals 0.37, right? So the intersection point, the location of point 2 will be 0.45 and 0.37. Okay, now let's go back at the code and let's look at how we can generalize this. Okay, so here I initialize our starting point. Right. So here is the x naught and y naught location right here. Okay. Now for point 1, I found y1 is 0 and x1 is 0.3. Right. So let me go back to point 2 case, basically this case right here. Right. Again, all I did here is basically code x2 and y2 equation. Right. And you just have to take care of what slope you end up using. So you get the slope angle, you know the slope of 1, 2, and then you know the slope of A2, right? So make sure you use the right slope in this, and when you run it, basically that's it, that's what you end up getting. Now, say for example, if you want to know the location of point 3, then all you gotta do is change 6, you know, it's theta A. Then we're incrementing by 3 degrees, right? So, well, there you go. You get the new location of, well, it's not x2 anymore, it's x3, but you get, you know, you get the idea, right? So now what we will do is we will, you know, you do for all these. Let me maximize this. Okay. So you'll be able to find all the value, all the coordinates of 1 to 7 points, right? Now we have to know what is the coordinate of the wall point is, right? I mean, I put it here, but let's talk about how you actually get that value, right? We know that the max angle deflection will be 0.375 at the throat, right? And we calculated the slope of 6, 7, basically this line to be 53.7 degrees. Now, for simplicity's sake, we can assume that the slope 7, 8 is actually equal to, I didn't mean to do that, but anyway, the slope 7, 8 will be equal to slope 6, 7. So basically these two lines have, this line and this line have the same slope, right? So when you do that, you can assume that's 53.7. Then all you gotta do is use the same equation we used before to calculate this this location of 0.8. Right? So when you do that, you will actually get about 1.7, 1.59. Again, guys, this is only with respect to like 7 mark lines, and it only works for the divisions that we actually set right here, right? So all of this is great, but still, we need, I don't want to keep changing the values every now and then, right? If I want to automate this, then I need a way to actually generalize this even more, right? So let's look at the trends here from 2 to 7, right? When I look at the trends, let's look at the CA and C+1 for a second, because CA is the right running characteristics, and C1 is the left running characteristics, right? Well, you see some common trends. So it looks like the theta A and mu A is the same for C minus A, right? And for C plus characteristics line, it's the same. Theta A equals mu A, or theta 1 equal mu 1, theta 2 equal mu 2, and so on and so forth, right? So I can generalize this, right? So let's look at how we can do that. Now I'm gonna just go over this point by point, right? So I'm setting my initial conditions, and I'm finding out what is a Prandtl-Meyer function for a given Mach number, and dividing that by 2. The reason how I do that, because that's my maximum. So that's my maximum deflection angle that I want to get, right? So I know what my dt is. Now I'm dividing the entire deflection in equal intervals of 7. So each interval we'll have about 2.62 degrees the flow will turn, right? Now here is an interesting part. So my theta is, I can set it equal to nu. Again, if you look in all these cases, theta will always be equal to nu no matter what. So I can actually set that, right? Now, my CMA, or C minus characteristic line, I'm adding theta and nu, right? So let's do that. Let's create a C minus characteristic line by adding theta plus nu. And let's do the C plus characteristic line, which is basically theta minus nu. When I do that, you can actually see this is my C plus, and we have values just like what we have here, and the C plus values are 0, right? Which is exactly what you need. And when you look at the Mach angle, it looks like we are simply finding the Mach angle of whatever the theta value we end up getting, right? So, hey, that's even great. So let's look at nu right there, right? Now you have everything you need. You found out just by using these few lines of code, you found out the Mach angles and theta and nu values in basically all these 7 locations, which is great, right? Now you can continue the same thing. Remember how we programmed this, the slope before? Same way you can program for point 1. Now I broke it down to point 1 to point 2 onwards, just so that you can understand it a little better, right? So point 1, point A is pretty simple. Let's look at point 1. So point 1, I'm basically automating this right here, right? I know my y1 is 0, right? And my x1 is 1 minus the slope. And the slope was about minus 73.3, but I wanted to program this so that it takes in whatever the value that I put in, right? So in order to understand that, how we can code, when I look at guys, this is again a very interesting part. So look at the slope of the the C, or is this the C minus curve right here, right? So you get theta A plus theta 1 and half of that, and for most part theta A will be equal to whatever the point that you're looking at, right? So in the end, what will really comes down to is theta minus mu, right? Because, well, the average of this is basically 73.7. The average of this will be 0.375, which is basically theta, which is then this is basically mu, right? So you can code it as y naught by tan d minus of tan d of theta minus mu, right? Which is basically the same equation right here, right? So that's point 1. So you get x naught and y naught of point 1. Again, mind you, you won't get 0.3 because now we are dividing it with equal intervals, right? We're not setting the first angle as 0.3 and then stepping in 3 increments. We're taking that 18.3 and just dividing it equally by 7, right? So in that case, you end up getting x as about 0.65, right? That's fine. So now from point 2 onwards, you can actually automate this or code this. Again, everything else is the same. You are basically coding these 2 equations, right? Let's look at the slope right here. So 0.5 is the characteristic line that comes from point A to all these different points, right? Now let's just look at this equation alone, right? That's the first equation right here. So for the most part, it looks like our theta A equals theta 6 and our mu A equals mu 6, right? So looks like our theta A looks like it's 15.375 degrees. That's my theta A. And look at the theta 6 is also 15.375 degrees, right? So when I put this in a loop, I'm going to state theta I plus theta I minus mu I plus mu I, right? That makes sense, right? And then we put it in the tan d so that you can get the actual slope. Now I found, by this line in the code, I found the slope of all these lines coming down. Okay. Now I want the slope from 1 to 2, 2 to 3, 3 to 4, and 4 to 5. So how do I do that? Well, let's look at this line right here. So no matter what point you look at, the way you can generalize this slope equation is by half of theta minus 1. So whatever the parameter, whatever the point of your interest, you're taking the point before it, and then you're adding that, right? So theta minus 1 plus theta times mu minus 1 plus mu, right? So you automate that. And next step, once you find the slopes, you need to find x and y locations, right, of these points right here. I mean, you can do this individually and calculate what x and y locations are, but you can just simply put this in the for loop, right? Again, no magic here. All I just coded with this equation that you see right here. Y minus, again, if you want x2, then you need the y location of the previous case. So y minus 1, 1 times y naught times, this is s2, the slope, times x I minus 1, right? Because you want the previous x location, which is 0.1 right here, right? Divided by s1 minus s2, and yi1 equals basically s2 times x2, which is xi. Again, this value and this value is the same, right? Minus x minus 1 plus yi minus 1. All right. So when you do that, you will get x and y locations of each and every single point, right? And the same way, you can actually find the wall slope, just like how we talked about earlier, right? So all that is left is just for you to plot the points, okay? So I plotted the points right here, but let me just remove this so that you can actually see. Right. So once you find the x and y locations, right, you can now see that there is the wall right here. It's 1 to 2. Just by using one of the the left running characteristic line, we calculated just what that one slope will be, right? This is the wall. This right here is the wall, and these are all the points that we have. Where is that? That we have right here, right? It's basically in the graph. So now, what do you do? What you're going to do is you do the same thing, but you consider the second left running characteristic line. Okay. So, and again, the equations are the same. The way you code is all the same. There's nothing else, changes. So hopefully this makes some sense on how you can actually code this method of characteristics line. Again, guys, it's not terribly complicated, but all you have to do is just keep track of your locations and your slope. If you can do that, it just comes down to plotting lines in MATLAB. All right, now I'm going to sleep. Bye. Oh, let me know if you have any questions, right?